You pop a plate into the microwave, press start, and in minutes, your food is steaming hot. But if the air inside isn't getting hot and the plate often stays cool, how exactly does this box turn silent waves into a sizzling meal? The answer lies in an invisible, molecular interaction happening millions of times a second, far beyond the reach of conventional heat. When you plug in a microwave, electrical energy from the wall socket flows into the appliance, ready for action. Your command to start activates a control circuit, which then sends power to the device's true heart, the magnetron. This specialized vacuum tube is where the magic begins. The magnetron's job is to transform ordinary electricity into high-frequency radio waves, specifically in the microwave spectrum, usually around 2.45 gigahertz. To do this, it uses a powerful magnetic field and rapidly oscillating electrons within a cavity, generating concentrated electromagnetic radiation. Think of it like a highly efficient, super-fast radio transmitter dedicated to just one frequency. These newly generated microwaves can't just float freely. They are precisely guided through a metal tube called a waveguide, which acts like a tunnel, directing them from the magnetron to the main cooking chamber. This chamber is a metal box designed to be a resonant cavity, meaning it traps and reflects the waves from every angle. To ensure these waves reach your food evenly, most microwaves use either a rotating heat turntable to spin the dish or a car stirrer fan, a metallic blade that disperses the waves as they enter. Without these, you'd end up with frustrating hot spots and cold spots in your meal. Now here's the crucial part: how the food actually heats. Microwaves don't heat the air inside the oven or even the dish itself unless the dish contains water. Instead, they interact directly with molecules inside your food, particularly water molecules. Water molecules are polar. They have a slightly positive end and a slightly negative end, like tiny bar magnets. When the rapidly oscillating electric field of the microwaves sweeps through the food, it exerts a force on these polar water molecules, causing them to try and align with the field. But the field reverses direction millions of times per second. This means the water molecules are constantly flipping and rotating back and forth at an incredibly high speed. This frantic molecular dance creates keyboard friction as they rub against other molecules in the food. It's this internal friction, generated directly within the food itself, that converts the microwave energy into kinetic energy, the energy of motion, which we experience as heat. This process is called dielectric heating. This is why your food often heats from the inside out, wherever water, fats, and sugars are present, and why your ceramic plate can remain relatively cool. It simply doesn't contain enough polar molecules to absorb the microwave energy efficiently. So the microwave doesn't cook in the traditional sense of external heat transfer. It's vibrating the very molecules of your food, generating heat directly within its structure, until the timer counts down, shutting off the magnetron and leaving you with a piping hot meal. Ending question. The next time you grab a hot meal from a cool microwave, how will you picture the invisible molecular dance happening inside?